Think about the television you watched when you were a kid. Like that old, heavy, standard definition box sitting in the corner of your living room.
Oh, yeah, the ones where the picture was all static.
Right, exactly. The colors were a bit muddy, the picture was static, and if you got too close, the fine details just dissolved into those blurry pixels.
Yeah, that's a good way to put it.
Well, that muddy, static picture is exactly what your childhood understanding of dinosaurs looks like. You learned about these sluggish, tail-dragging, swamp-dwelling gray and green lizards that were somehow just, evolutionary failures waiting for an asteroid to put them out of their misery.
Which is just so fundamentally wrong.
It is. So today we are upgrading you to an 85-inch 4K resolution OLED display. We are going to completely dismantle that outdated pop culture image and rebuild your understanding of these creatures as dynamic, highly adaptable, incredibly complex animals.
They really dominated the Earth for millions of years.
Exactly. And by looking at the staggering amount of paleontology, biomechanics, and evolutionary biology we have piled up on the desk for today's deep dive, we are going to prove to you that the age of dinosaurs never actually ended.
It really is a profound shift in perspective. I mean, when we look at the overarching consensus in modern paleontology, the most crucial fact we have to establish right from the jump is that dinosaurs are not entirely extinct.
Wait, not entirely.
Right. The science draws a very hard, biologically vital line, dividing them into two distinct groups. So you have the extinct non-avian dinosaurs, and you have the living avian dinosaurs.
And by avian dinosaurs, we are talking about birds.
Yes, exactly.
Birds. I want to make sure you, listening right now, really internalize that. Birds aren't just related to dinosaurs. They aren't descendants in some, loose metaphorical sense. A pigeon, a hawk, a penguin. They literally are dinosaurs.
Yeah, the numbers on this are just staggering.
They are. Today, there are over 11,000 living species of birds on Earth. Now compare that to the entirety of the fossil record. Paleontologists have confidently identified roughly 900 non-avian dinosaur genera from the Mesozoic era.
Right.
So 900 extinct genera compared to over 11,000 living species today.
Which completely vaporizes that whole narrative that dinosaurs were an evolutionary failure.
Yeah.
I mean, just by sheer numbers and diversity alone, they are one of the most successful groups of terrestrial vertebrates currently living on the planet.
Absolutely.
They conquer every environment, you know, from the deep ocean where penguins hunt to the upper atmosphere where bar-headed geese migrate over the Himalayas.
But establishing that birds are dinosaurs kind of forces us to confront a fundamental question, right? Like, what actually makes a dinosaur a dinosaur?
That's the big question.
Because if a hummingbird is a dinosaur, but a massive, terrifying prehistoric marine reptile is not, how is modern science drawing those lines? Like growing up, I had this big plastic tub of dinosaur toys.
Oh, we all did.
Right. And I had a Triceratops and a T-Rex, sure. But I also had a pterodactyl, a flying pterosaur, and a plesiosaur, the marine reptile with the long neck and the four flippers.
Yeah, the classic toy box mix.
I even had a Dimetrodon, that lizard-like creature with the massive sail on its back, and my toy box just dumped them all into the dinosaur category. So why aren't they dinosaurs?
Well, pop culture really prioritizes aesthetics. If it looks like a big, scaly, extinct monster, we just call it a dinosaur. But biology prioritizes anatomy and shared ancestry.
Okay, so what's the actual biological definition then?
To be classified as a dinosaur, an animal must possess specific anatomical modifications. We call these synapomorphies. They're evolutionary innovations inherited from a common ancestor.
Like what?
There are about a dozen of these highly specific markers in the skeleton, but the most critical one for understanding how they conquered the world actually relates to their posture, specifically the architecture of their hips and hind limbs.
So the hips don't lie.
They really don't. So dinosaurs belong to a larger group of animals called archosaurs, which includes crocodiles.
Okay.
But if you look at a typical reptile like a crocodile or a Komodo dragon,
Yeah.
their legs sprawl out sideways from their bodies. Their belly is really low to the ground.
Right, they do that weird waddle.
Exactly. Dinosaurs, however, evolved a completely different biomechanical solution. They hold their limbs entirely erect beneath their bodies.
Kind of like how mammals do it.
Yes, like a horse or a dog. But dinosaurs achieved this through a very specific modification in the pelvis. They developed an open socket in the hip, a literal hole in the bone called an open acetabulum.
Oh, wow.
And they had this inwardly facing barrel-shaped head on the thigh bone, the femur, that slotted perfectly into it.
Let me try to visualize this. It's like the difference between doing a push-up with your elbows flared way out to the sides, almost touching your ears, versus doing a push-up with your arms tucked right under your chest.
That's a perfect mechanical analogy.
Because holding your weight out to the sides takes massive muscular effort just to keep your belly off the floor. But tucking your limbs underneath you transfers that weight directly into your skeletal columns.
Right, but the advantage of this erect posture goes way beyond just supporting massive weight. It fundamentally changed how they breathed.
Wait, how does standing differently change how you breathe?
There's this physiological limitation in sprawling animals known as carrier's constraint. When a sprawling reptile walks or runs, its body bends from side to side in an S shape.
Okay, yeah, I can picture that.
That side-to-side motion actually compresses one lung while expanding the other, effectively moving stale air back and forth between the lungs instead of pulling fresh air in from the outside.
Oh, so they're basically just sloshing the same air around.
Exactly. That means the sprawling reptile physically cannot breathe efficiently while it's running. It has to sprint, hold its breath, and then stop to pant.
Which is exactly what you see an iguana or an alligator do. They move in short, explosive bursts, and then they just freeze.
Precisely. But because dinosaurs tucked their legs directly underneath their bodies, their forward motion was generated entirely by the swinging of their legs, not by the undulating of their torso.
So their chest stayed still.
Right. Their rib cages remained completely stable while they ran. This freed up their respiratory system, allowing them to take deep, continuous breaths while moving at top speed.
Wow.
It permitted a level of cardiovascular stamina and sustained activity that just completely outclassed the sprawling reptiles of their time.
That one anatomical change totally shatters the sluggish lizard myth right from the start. But wait, what about the Dimetrodon with the sail? The one from my toy box?
Ah, right. Dimetrodon lived tens of millions of years before the first dinosaur even existed. And more importantly, it isn't even a reptile. It's a synapsid, which is an entirely different branch of the evolutionary tree that eventually led to mammals.
Are you saying I'm more closely related to a Dimetrodon than a T-Rex is?
You absolutely are.
That is wild. What about the flying ones and the swimming ones?
Pterosaurs are close cousins to dinosaurs, but they lack that specific open-socket hip anatomy. And marine reptiles like plesiosaurs and ichthyosaurs are even further removed. They're reptiles that return to the sea, completely unrelated to the dinosaur lineage.
Got it.
Under modern phylogenetic nomenclature, classification is strictly about family trees. The clade Dinosauria is formally defined as the group consisting of the most recent common ancestor of Triceratops and modern birds and all of its descendants.
So it's a very strict, highly precise biological club.
Very strict.
But it took us a massive amount of time to actually define the parameters of that club, right? Because these bones didn't exactly come out of the ground with phylogenetic labels attached to them.
Definitely not.
For thousands of years, humans were tripping over these massive skeletons with absolutely zero scientific context.
And, human beings, when confronted with the inexplicable, we do what we do best. We invent mythologies.
Oh, for sure.
Long before the framework of paleontology existed, these fossils were deeply penetrating human culture. In China, for instance, dinosaur remains were widely documented as dragon bone.
Dragon bones?
Yeah, they were considered to have immense pharmacological value and were ground up and used in traditional medicine. There are actually regional gazetteers dating back to the 3rd century, specifically mapping out where to find these dragon bones.
What blows my mind is that this isn't just ancient history. We have reports from as recently as 2007 in a village in Henan province, China, where locals had spent decades actively excavating real, scientifically priceless dinosaur bones and selling them by the pound for traditional medicine.
Yeah, it's wild. They truly thought they were flying dragons.
Meanwhile, in Europe, the interpretation was completely different, but equally steep in myth. They looked at these bones and saw biblical giants.
Right, which brings us to the late 17th century in England. In 1676, a piece of a truly massive bone was recovered in a limestone quarry in Oxfordshire. It was sent to Robert Plot, who was the first professor of chemistry at Oxford University. Plot was a brilliant man for his time. He correctly identified the bone as the lower extremity of a femur, a thigh bone.
But he didn't look at it and say, oh, a bipedal Mesozoic archosaur.
No, he had absolutely no concept of deep time or extinction. He measured the circumference of the bone, compared it to an ox and a horse, and realized it was far too massive to belong to any known animal in England.
So what did he think it was?
Relying on the accepted historical framework of his day, he concluded it must be the femur of a huge human being, perhaps a titan from classical mythology, or a giant mentioned in the Bible.
Unbelievable.
We know now, based on his precise illustrations, that it was actually the femur of a megalosaurus, which is a large predatory theropod. And shortly after that, in 1699, Edward Lude described a tooth found in Oxfordshire, naming it Rutellum implicatum.
And what was that actually from?
We now recognize that tooth as belonging to a massive, long-necked sauropod.
It's like a medieval peasant finding a microchip in the dirt. You just simply don't have the paradigm to understand what you're holding.
Exactly.
But then, in the 19th century, the scientific method finally catches up to the mythology. Sir Richard Owen steps onto the scene in 1842, and he fundamentally changes the game. He's the one who coined the term dinosauria.
Yes. Owen was a brilliant, albeit notoriously difficult, English anatomist. He examined the scattered fossils of Megalosaurus, Iguanodon, and an armored creature called Hylaeosaurus.
Right.
And he noticed that their teeth and their posture didn't match modern lizards. They had fused sacral vertebrae at the base of their spine, reinforcing their massive hips. He realized they weren't just overgrown iguanas, they belonged to a distinct, previously unrecognized tribe of ancient reptiles.
And that's when he came up with the name.
Right. He constructed the word from the ancient Greek roots Dinosaurs.
Fearfully great lizard. And I want to point out something really nuanced here that the sources mention. Today, when we hear fearfully great, we think of a monster movie. We picture razor-sharp teeth, blood, and terror.
Of course.
But Owen wasn't trying to evoke a horror story. He was a Victorian scientist trying to capture their sheer majesty, their biological success, and their unimaginable scale. He meant fearful in the sense of awe-inspiring.
Absolutely. He was recognizing them as the apex of reptilian evolution. And giving them a name, grouping them into a formal scientific category, sparked a global frenzy.
It validated them.
Exactly. It validated them as real historical animals, which led directly to an explosive era of discovery in North America known as the Bone Wars.
If there was ever a period of scientific history that deserves a 10-part dramatic miniseries, it is the Bone Wars.
Oh, without a doubt.
This wasn't a bunch of quiet men dusting off rocks in a laboratory. This was the Wild West.
It was a bitter, decades-long, highly destructive rivalry between two prominent scientists, Edward Drinker Cope from the Academy of Natural Sciences in Philadelphia and Othniel Charles Marsh from Yale.
And they just hated each other.
Starting in the 1870s, they engaged in an all-out war to discover, name, and hoard more dinosaur species than the other. They sent armed teams into the American West, particularly into the fossil-rich Morrison Formation.
And their methods were completely unhinged. Like, when we think of paleontology today, we picture people with tiny dental picks and paintbrushes spending 3 weeks uncovering a single toe bone.
Right, taking meticulous notes.
But Cope and Marsh's crews used dynamite. If one team was leaving a quarry and knew the other team was coming, they would literally blow up the remaining fossils so their rival couldn't get them.
It is a profound tragedy for modern science. Blasting away the rock destroys the fragile fossil matrix. But more importantly, it destroys the vital stratigraphic evidence.
It was context.
Exactly. The specific layers of sediment that tell us exactly how old the fossil is, what the local climate was like, what other microscopic animals or plants lived alongside it. They threw away the context just to get the trophy.
That's so frustrating.
It gets worse. They also engaged in bribery, hired spies to infiltrate each other's camps, and rushed their publications to press with massive errors just to claim the naming rights.
Didn't Cope put a head on the wrong end of a dinosaur?
He did. He famously reconstructed an Elasmosaurus skeleton and accidentally placed the head on the tip of the tail.
Oh, no.
Marsh publicly pointed out the error, deeply humiliating Cope, which only poured gasoline on their feud.
It was chaotic, but we have to admit their obsession forced the field forward at absolute breakneck speed. Between the two of them, they unearthed 142 completely new species of dinosaurs.
That's a huge number.
They found the iconic ones we all know today: Stegosaurus, Apatosaurus, Triceratops, Allosaurus. Their private collections eventually became the foundational exhibits at the American Museum of Natural History in New York and the Smithsonian.
They absolutely filled the museums, which sparked massive public interest, often called dinosaur mania.
Yeah.
But despite having all these magnificent skeletons articulated in museum halls, the scientific interpretation of the animals remained surprisingly stagnant for the first half of the 20th century.
Why is that?
Because the animals were so massive, paleontologists just assumed they must have been slow, dim-witted, cold-blooded beasts that spent their lives wading in swamps just to support their own weight.
The muddy TV picture again.
Right. That narrative of sluggish evolutionary dead ends persisted until a massive paradigm shift in the late 1960s, a period we now call the dinosaur
The
renaissance.
dinosaur renaissance. This is where we finally wipe the mud off the screen. And it really kicks off with John Ostrom and a predator that completely broke the mold.
Yes. In 1964, Ostrom, who was a paleontologist at Yale, was exploring the Badlands of Montana when he discovered the remains of a medium-sized theropod dinosaur.
Okay.
He named it Deinonychus, which means terrible claw. And when Ostrom analyzed the biomechanics of this skeleton, the old sluggish lizard paradigm completely collapsed.
Why? What did the skeleton tell him?
Deinonychus was built for hyper-athletic performance. Ostrom saw a bipedal predator with long, lightly built legs suited for running. Its tail wasn't a heavy, dragging appendage. It was encased in a network of bony rods, ossified tendons that made it stiff and rigid.
Like a counterbalance.
Exactly, acting as a dynamic counterbalance, like the tail of a modern cheetah making a high-speed turn. But the most shocking feature was on its feet. On the second toe of each foot, it possessed a massive, highly curved, sickle-shaped claw.
The terrible claw.
Right. To use that claw effectively as a weapon, the animal would have had to leap into the air, balance on one leg, or grapple its prey with its hands while kicking.
And you cannot execute acrobatic leaping attacks if you are a cold-blooded lizard relying on the sun to warm up your muscles.
No, you can't.
You simply don't have the metabolic engine for it.
Exactly. Ostrom forcefully argued that to support this kind of highly energetic, agile lifestyle, Deinonychus had to have an elevated metabolism. It had to be endothermic or warm-blooded, internally regulating its own body heat.
Which was a huge deal at the time.
It was incredibly radical. But Ostrom's student, Robert T. Baker, took the concept and completely revolutionized the field with it. Baker published a series of aggressive, brilliantly argued papers asserting that all dinosaurs were active, warm-blooded terrestrial animals.
He really went to bat for them.
He did. He looked at predator-to-prey ratios in the fossil record, bone histology, upright posture, systematically dismantling the idea of the swamp-bound sauropod and replacing it with an image of vigorous, dynamic animals.
So Ostrom and Baker shifted the paradigm by looking at the mechanical engineering of the bones. But as we move into the 1990s and 2000s, this renaissance goes into overdrive.
Oh, definitely.
We stop relying solely on bones and we start finding things that shouldn't even exist. We enter the soft tissue revolution.
This is the era where paleobiology begins to read almost like science fiction.
Honestly.
For a century, the dogma in paleontology was that only hard tissues, bones, teeth, horns could survive the millions of years required to become a fossil. Soft tissues like skin, muscle, and feathers were thought to decompose far too quickly. But that dogma ignored the existence of specific, incredibly rare geological deposits known as conservation Lagerstätten.
Lagerstätten. I think that translates roughly to storage places, right?
Yes, mother lodes of preservation. These are sedimentary deposits formed under highly specific, perfect conditions. Imagine a deep, calm, volcanic lake.
Okay.
If an animal dies and sinks to the bottom of this lake, it enters an anoxic environment, a zone with absolutely no oxygen. Without oxygen, the bacteria that normally cause decomposition cannot survive. Scavengers cannot reach the carcass.
Wow.
The animal is then rapidly buried by incredibly fine, powdery volcanic ash settling at the bottom of the lake.
So it's essentially vacuum sealed in stone.
Vacuum sealed.
And the most famous of these sites are in China, right? The Jahal and Yongliao biotas.
Yes. The discoveries coming out of those Chinese deposits starting in the 1990s utterly transformed our understanding of the Mesozoic. Paleontologists began splitting slabs of shale and finding exquisite carbonized outlines of skin impressions, stomach contents showing exactly what the animal ate for its last meal.
Unbelievable.
And, most shockingly, highly detailed feather structures covering entirely non-flying dinosaurs.
Finding the shape of a feather pressed into rock is one thing. That tells us they were fluffy, which is a huge deal. But we didn't stop there. We figured out what color they were.
We did.
If you're holding a piece of gray rock that is 120 million years old, how on earth do you extract a color palette from it?
Well, it requires a deep understanding of cellular biology and light physics. In living animals today, coloration is primarily produced by pigment-storing cellular structures called melanosomes.
Okay.
And the physical shape of a melanosome determines the pigment it stores. For instance, if you look at a feather under a highly powerful electron microscope and see long, sausage-shaped melanosomes, those store eumelanin, which produces black or dark brown colors.
Like melanin in humans.
Exactly. But if you see spherical, Meatball-shaped melanosomes, those store pheomelanin, which produces reddish or ginger colors.
And those microscopic structures survived the fossilization process.
They did. For years, scientists saw these tiny structures in the fossilized feathers and assumed they were just the fossilized remains of ancient bacteria.
Oh, sure, that makes sense.
But in the late 2000s, researchers mapped the distribution of these structures and realized they were perfectly aligned within the structure of the fossilized feathers, exactly where melanosomes sit in modern bird feathers.
So they weren't bacteria at all.
No. By using scanning electron microscopes to analyze the shape and density of these fossilized melanosomes and comparing them to a database of modern bird feathers, paleontologists could literally reverse engineer the color of the dinosaur.
That is just an astonishing piece of scientific detective work. You are decoding a 120-million-year-old paint by numbers.
It really is.
And the results give us such a vivid picture of their ecology, like Sinosauropteryx, right? A small theropod dinosaur from China. The text says we now have a full-body color reconstruction of it.
We do.
It wasn't the drab gray lizard of the 1950s textbooks. It was covered in reddish-brown, ginger-colored fuzz. It had a long tail with alternating ginger and white stripes, like a lemur.
And most importantly, it exhibited countershading.
Countershade.
It's a very specific camouflage technique. It means the animal is darker on its back and lighter on its underbelly.
Oh, I see.
When sunlight hits a three-dimensional object from above, it naturally lights the top and casts a shadow on the bottom, which makes the object pop out visually. Countershading cancels out this natural shadow, flattening the animal's profile and making it much harder for predators or prey to detect it against the background.
So not only do we know its color, we know how it hid from larger predators.
Exactly.
And then there is Psittacosaurus, an early relative of the horned dinosaurs like Triceratops. We analyzed its melanosomes and found it also had countershading, but the pattern of its camouflage was highly specific to a closed canopy forest environment where light filters down through leaves.
Which is incredible detail. Oh, and the fossils also revealed it had a row of long, stiff, quill-like bristles running down its tail.
Like a porcupine.
Sort of, which
Yeah.
completely changes the silhouette of the animal. It proves that elaborate soft tissue display structures were actually really common.
But the soft tissue revolution went far deeper than just feathers and external colors. In 2005, a paleontologist named Dr. Mary Higby Schweitzer published a finding that challenged the very laws of chemistry and fossilization.
This was a massive moment.
Walk us through what she did, because this sounds completely impossible.
So Schweitzer and her team had a fragment of a femur from a Tyrannosaurus rex excavated in Montana, dating back roughly 68 million years. They decided to do something highly unusual.
Okay.
They took fragments of the bone core and placed them in a weak acid solution to dissolve away the mineral matrix, the calcium phosphate that makes the bone hard. The standard assumption was that once the minerals dissolved, there would be absolutely nothing left, because all organic material should have degraded millions of years ago.
But there was something left.
Yes. When the minerals dissolved, what remained was a soft, flexible, translucent tissue.
You're kidding.
They found intact branching blood vessels that were still elastic. They found the fibrous protein matrix of the bone itself. They even isolated microscopic structures inside the vessels that looked exactly like the nucleated red blood cells of modern ostriches.
Finding flexible 68-million-year-old blood vessels. I have to imagine the academic community did not accept this quietly.
Oh, the skepticism was fierce, and rightfully so. Extraordinary claims require extraordinary evidence.
Sure.
Many scientists argued that these flexible structures must be biofilms, layers of modern bacteria that had seeped into the fossil underground and taken on the shape of the empty blood vessel cavities.
But Schweitzer pushed back.
She did. Her team spent years systematically proving their case. They used mass spectrometry to analyze the molecular makeup of the tissue, and they found fragments of actual proteins, collagen, elastin, and laminin.
And collagen doesn't come from bacteria. That is an animal protein.
Exactly. They even managed to extract enough intact collagen protein sequences to run a phylogenetic analysis. When they compared the T-Rex collagen sequences to a massive database of living animals, the T-Rex grouped most closely with modern chickens and ostriches,
Wow.
completely independently verifying the dinosaur-bird link at a molecular level.
And it isn't just microscopic proteins. We found macroorgans. The source mentions a fossil from Italy, a small juvenile theropod named Scipionix.
Scipionix is a miraculous specimen. It died in an environment that perfectly preserved its soft anatomy. We can literally see its internal organs.
Really?
Yeah, the fossil preserves the trachea, the windpipe, it preserves muscle tissue. We can clearly map the intestines, the colon, and a large red stain that represents the iron-rich remains of the liver.
And seeing those organs tells us how the machine operated.
Absolutely. By looking at the size and position of the intestines, we know that their digestive tracts were incredibly short and wide compared to herbivores, optimized for the rapid, high-efficiency processing of meat.
So if we step back and look at what we've assembled, we have an animal with the energetic, warm-blooded metabolism of Ostrom's deinonychus.
Right.
We have the complex structural feathers and camouflage of Sinosauropteryx. We have the bird-like collagen and blood vessels of Schweitzer's T-Rex. We are mapping a highly complex avian biology onto these creatures.
Which is amazing.
But here's the massive question. How does that highly active bird biology respond when you scale it up to the size of a building? Because a 100-ton bird presents an enormous mechanical and thermodynamic problem.
That's the real puzzle. The extremes of scale achieved during the Mesozoic era are just unparalleled in the history of life on Earth. To understand just how bizarre this is, we have to look at the mammalian baseline.
Okay.
We live in the Cenozoic era, the age of mammals. Today, the most common body mass for a terrestrial mammal is somewhere between 2 and 5 kilograms.
Basically the size of a domestic cat.
Right. We look at an elephant and think that's normal, but elephants are extreme evolutionary outliers today. Most mammals are rodents, bats, and small carnivores.
Yeah, that makes sense.
But during the Mesozoic, the rules of biology operated on an entirely different scale.
Mm-hmm.
The mode, the most common body mass for a dinosaur across its entire 160 million year reign, was between 1 and 10 metric tons.
That is 1,000 to 10,000 kilograms. So the average dinosaur walking around was the size of a rhinoceros or a large African elephant.
Yes, and that's just the average.
Let's talk about the titans, the long-necked sauropods.
The sauropods pushed the absolute limits of biological engineering. They were an order of magnitude more massive than any other terrestrial animal in history. The research points to Giraffatitan, a brachiosaurid, whose mounted skeleton in Berlin stands 12 meters tall.
Huge.
And you have Patagotitan, whose skeleton mount in New York stretches over 37 meters long. That's longer than 3 school buses parked end to end.
But the text we are looking at mentions a name that is currently causing absolute shockwaves in the paleontological community. Bruaphcaesaurus.
Right. Bruaphcaesaurus is a highly controversial taxon. Its fossils were originally discovered in India in the late 1980s. Tragically, the original bones were poorly preserved due to monsoons and were subsequently lost or destroyed.
Oh, that's terrible.
For a long time, it was considered a dubious species. However, recent archives photographs and field notes from the original excavation were uncovered and analyzed in 2023, confirming the massive dimensions of the limb bones.
Give me a sense of the scale we are talking about here.
The estimates derived from these newly analyzed records are almost incomprehensible. Paleontologists suggest Bruaphcaesaurus could have reached lengths up to 44 meters, and its weight, its mass, is estimated to be in the range of 110,000 to 170,000 kilograms.
170,000 kilograms. Okay, let's put that in perspective for you listening. A fully loaded Boeing 747 airliner, fueled up and full of passengers, weighs roughly 180,000 kilograms.
It's staggering.
We are talking about a living, breathing animal walking on 4 legs that weighed as much as a commercial jet. It challenges the structural limits of bone and muscle. It rivaled, or possibly exceeded, the blue whale as the largest and heaviest animal to ever exist, land or sea.
It did. And yet, on the exact opposite end of the spectrum, the biological plasticity of this group is equally astounding.
Oh.
The smallest known dinosaur is not extinct. It is alive today. It's the bee hummingbird, which measures just 5 centimeters long and weighs 1.8 grams.
1.8 grams?
Yeah. Even in the Mesozoic, you had extinct non-avian dinosaurs like Anchiornis that were the size of a pigeon, weighing about 110 grams. To have a single genetic lineage capable of producing a 1.8-gram hovering nectar drinker and a 170-ton terrestrial titan is an evolutionary miracle.
But the mechanics of those titans are what fascinate me. Gravity is a relentless enemy, and metabolism requires fuel.
It certainly does.
If you weigh 100 tons, how do you eat enough calories to keep your massive heart beating? You can't spend all day chewing leaves.
You don't chew at all. The secret to the sauropod's immense size was a radical simplification of their head and an extreme specialization of their gut.
Okay.
If you look at a sauropod skull, the teeth are very simple, peg-like or spoon-shaped structures. They lack the complex grinding molars of mammals, Their heads were basically just biological rakes.
Biological rakes?
Right, they stripped entire branches of pine needles, cycads, and ferns, and swallowed massive quantities of low-nutrient plant matter completely unchewed.
So the head is just a funnel. But how do you get calories out of a pine needle if you don't chew it?
By using sheer volume and time. I know you've used the analogy of an industrial fermentation vat, and functionally that is exactly what a sauropod torso was.
Just a giant vat.
Because their bodies were so massive, their digestive tracts were incredibly long. The unchewed plant matter would sit in their massive barrel-shaped guts for weeks, where a complex microbiome of bacteria fermented it, slowly breaking down the tough cellulose and extracting every possible calorie.
Oh, wow.
By not wasting time chewing, they could feed constantly, maximizing their caloric intake.
Okay, so the fuel problem is solved by the fermentation vat. But what about the heat problem?
Right.
Because if you have an active metabolism and you weigh 100 tons, you are generating a massive amount of internal body heat. An elephant today struggles to stay cool, and it uses giant ears to radiate heat. A sauropod is 30 times larger than an elephant. Why did they literally cook from the inside out?
Well, if a sauropod had a respiratory system like a mammal, it absolutely would have overheated and suffocated. Mammals have a bidirectional respiratory system. We pull air into our lungs down a dead-end path, the alveoli. The oxygen enters the blood, the carbon dioxide is released, and then we have to push that stale air back out the exact same way.
Right, which isn't very efficient.
It's highly inefficient because fresh air is constantly mixing with stale air.
So how did the dinosaurs fix it?
Saurischian dinosaurs, which include the massive sauropods and the two-legged theropods, evolved a unidirectional respiratory system completely identical to modern birds. They developed a network of biological balloons called air sacs that extended out from the lungs.
Wait, balloons inside their bodies?
Yes, ranging from the neck down into the abdomen. And incredibly, these air sacs actually invaded the bones. They entered the vertebrae, hollowing out the core of the skeleton, creating what we call pneumatic bones.
Oh, wild.
This system allowed for a continuous one-way flow of fresh air through the lungs. When a dinosaur inhaled, fresh air went into the rear air sacs, while the air already in the lungs moved into the front air sacs.
Okay.
And when it exhaled, the fresh air from the rear sacs was pushed through the lungs. This meant the animal's lungs received a continuous stream of oxygen-rich air on both the inhale and the exhale.
That is an unbelievable biological engine.
It really is.
Yeah.
It accomplished three vital things that allowed gigantism. First, the hollow air-filled bones dramatically reduced the overall weight of the skeleton, allowing them to grow massive without collapsing under their own density.
Makes sense.
Second, the continuous oxygen flow provided the massive aerobic power needed to move a 100-ton body. And third, and most importantly for your question, it acted as an internal air conditioning system. All that rapid airflow through the core of their bodies, directly against their internal organs and inside their spine, wicked away the excess metabolic heat and vented it out through their breath.
So they were basically liquid-cooled or air-cooled rather from the inside.
Exactly.
Which brings us to the great debate. Were they warm-blooded or cold-blooded? We know Ostrom argued for warm-bloodedness, but where does the modern consensus land?
The scientific consensus has settled into a highly nuanced middle ground termed mesothermy. Most dinosaurs generated their own internal heat, putting them well above the metabolic rates of cold-blooded modern reptiles. But they probably didn't burn energy quite as hot or as fast as a modern mammal or a small bird.
So they were somewhere in between.
Right. They existed in a highly efficient intermediate metabolic space. However, for the gargantuan sauropods, their sheer size completely changed the thermodynamic rules.
How so?
It's a principle of physics called the square cube law, which dictates an animal's surface area to volume ratio. As an animal gets larger, its internal volume increases exponentially faster than its external skin surface area.
Okay, I'm tracking.
So a 100-ton Brachiosaurus has an unimaginable amount of volume generating heat, but relatively little skin surface area through which to lose that heat. They were gigantothermic.
Meaning their size kept them warm.
Yes. Their massive bulk essentially trapped heat like a thermos. They didn't need a blazing fast mammalian metabolism to stay warm. Their size alone kept their internal temperature highly stable, even if the outside air cooled down at night.
It is brilliant, incredibly efficient biological engineering. We have taken these animals out of the swamp. We've given them high-performance respiratory systems, we've covered them in vibrant, structurally colored feathers, and we understand the thermodynamics of their massive scale.
It's a totally different picture.
But an animal is more than just its plumbing. Now we have to look at how they lived. What was a day in the life of a Mesozoic dinosaur actually like? Let's talk about behavior, because this is where a lot of our pop culture assumptions completely fall apart.
Oh, absolutely. Behavior is notoriously the most difficult aspect of an extinct animal to reconstruct, because behavior doesn't fossilize. A bone can tell you how an animal walked, but it can't definitively tell you how it socialized.
Right.
However, the field of taphonomy, the study of how organisms decay and become fossilized, has provided some spectacular, albeit complex, clues.
Okay, let me ask the question everyone wants to know.
Let's hear it.
Every movie, every documentary loves to show predatory theropods, like Deinonychus or Velociraptor, hunting in highly coordinated mammal-like packs. They show them operating like wolves, they have an alpha, they communicate with head nods, they strategically flank a larger prey animal, hamstring it, and bring it down together.
Right, the classic movie scene.
Does the actual science back that up?
This is a massive point of contention in paleontology, but
Okay.
the strict answer is we need to be incredibly careful not to project mammalian behavior onto archosaurs.
So probably not like wolves?
The evidence for wolf-like pack hunting is, at best, circumstantial, and at worst, a complete misinterpretation of the data. Now, to be clear, there is absolute indisputable evidence of gregarious herding behavior among herbivorous dinosaurs.
The plant eaters.
Right. We have vast trackways showing hundreds of horned dinosaurs moving together. There's a famous site in a coal mine in Bernissart, Belgium, where 31 adult iguanodon skeletons were found jumbled together, having perished simultaneously in a deep, flooded sinkhole. So the plant eaters definitely lived in herds.
Which makes sense for prey animals. There is safety in numbers. But what about the meat eaters? What is the evidence that Deinonychus hunted in packs?
Well, the theory originated from taphonomic death assemblages. Paleontologists would find a massive herbivorous dinosaur, like a Tyrannosaurus, dead, surrounded by the fossilized remains of several smaller Deinonychus individuals, along with dozens of shed predator teeth.
Seems like a smoking gun.
It does. The initial romantic interpretation was that a pack of Deinonychus attacked the larger herbivore together, and several of the predators were killed in the struggle before the pack ultimately brought the prey down.
But modern researchers look at that same crime scene and see a different story.
Yes. They look at the closest living relatives of dinosaurs, birds, and crocodiles. Highly coordinated cooperative pack hunting is incredibly rare in modern archosaurs. It exists in some birds, like Harris's hawks, but it is the exception, not the rule.
Okay.
A much more biologically plausible explanation for those death assemblages is mobbing behavior, similar to what we see in Komodo dragons or crocodiles today.
How does mobbing work?
A large herbivore dies of natural causes, gets stuck in the mud, or is killed by a single large predator. The smell of the carcass attracts dozens of smaller predators from miles around. They don't know each other. They aren't a family unit.
They just all show up for the buffet.
Exactly. They all swarm the carcass to feed, and in the ensuing frenzy, they become highly aggressive toward each other. The larger predators attack the smaller ones to monopolize the meat. The dead Deinonychus found around the Tenotosaurus weren't killed by the prey. They were likely killed by their own kind in a violent dispute over a free meal.
Wow, so it's less like a highly coordinated wolf pack and more like a bunch of aggressive crocodiles violently thrashing and biting each other over a dead hippo?
Exactly. It's a much more chaotic, brutal reality. And the evidence for theropods engaging in severe interspecific combat fighting their own kind is extensive.
Like what?
We have tyrannosaur skulls covered in deep healed bite marks that perfectly match the teeth of other tyrannosaurs. We even have confirmed taphonomic evidence of cannibalism. The bones of the large theropod Majungasaurus, found in Madagascar, show deep-toothed scores that could only have been made by another Majungasaurus. They were actively eating each other.
Brutal. But even if they were solitary and aggressive, they still had to communicate. They had to defend territory. They had to attract mates.
Right.
If they aren't coordinating hunts with vocal barks, how are they talking to each other? Did a T-Rex stand on a mountain and let out an earth-shattering lion-like roar?
Almost certainly not. A mammalian roar is produced by a larynx with highly specialized vocal folds, vocal cords that mammals possess. Dinosaurs evolved entirely different structures. First and foremost, visual communication was paramount.
With feathers?
Think about the incredible, bizarre diversity of soft and hard tissue structures we've found. The massive bony frills of the ceratopsians, the elaborate crests of the duck-billed hadrosaurs, the vibrant, counter-shaded feathers of the theropods. These were visual billboards, used to signal age, health and species identity to rivals and potential mates.
But they weren't silent. The forest wasn't quiet.
No, they're certainly acoustic animals. But the sounds they made were completely different from mammalian roars. We look at modern archosaurs again. Crocodiles don't roar. They produce deep guttural bellows.
Right.
And many large ground-dwelling birds like ostriches and cassowaries produce incredibly deep, low-frequency booming sounds. A 2016 study analyzing the anatomy of dinosaurs and modern birds concluded that many dinosaurs likely engaged in closed-mouth vocalizations.
Closed mouth, like humming.
Similar in mechanics, but vastly different in scale. They likely kept their jaws shut and pushed air into inflatable esophageal or tracheal pouches in their throats and necks. This generated deep, resonating booms, hoots, and coos.
Whoa.
And low-frequency sound is incredibly effective in dense environments. High-pitched sounds get absorbed by trees and leaves. Low-frequency bass thrums travel for miles through dense jungle undergrowth.
Wait, I remember reading about the crests on the duck-billed dinosaurs. Those crests were hollow.
Yes, the hadrosaurs, like Parasaurolophus, had massive, hollow, bony tubes extending from the back of their skulls. Those tubes connected directly to their nasal passages. When they forced air through those elaborate loops, the craft acted like a massive resonating chamber.
Like a trombone or a French horn.
Exactly, amplifying those low-frequency sounds over massive distances. And we now have direct fossil evidence of their vocal organs. Paleontologists recently discovered a fossilized larynx in an ankylosaurid called Pinacosaurus, which shows highly complex, specialized bones, suggesting they were capable of very nuanced bird-like vocalizations. Furthermore, we've found the fossilized remains of a syrinx, the unique two-barreled vocal organ that gives modern birds their incredible singing ability in a late Cretaceous duck-like bird called Vigavus.
It paints such an eerie, magnificent picture. Instead of a jungle full of mammalian roars, the Mesozoic forest is vibrating with these deep, bass-heavy thrums, booms, and complex honks.
Yeah, it completely changes how you imagine it.
Okay, so we have them booming at each other, fighting over carcasses and flashing their bright feathers. What about family life? We talked about cannibalism and violence, but did they have a softer side? Did they raise their young?
They absolutely did, and the science behind how we know this is fascinating. It starts with the egg itself. A major breakthrough occurred regarding how female dinosaurs physically prepared for reproduction.
Okay.
When a modern female bird is getting ready to lay eggs, she has a massive physiological problem. She needs a huge amount of calcium to build the hard egg shells, and she needs it fast.
Makes sense.
To get it, she actually draws calcium out of her own skeleton, depositing a temporary spongy layer of bone tissue inside the hollow cavities of her long bones, like the femur. This is called medullary bone.
It's basically a highly accessible biological bank account for calcium.
Exactly. Osteoclasts break down the regular bone, and osteoblasts build this temporary medullary bone, which is rapidly depleted as the eggshells form. For a long time, this was thought to be a uniquely avian trait. But then, scientists sectioned a fossilized femur of a Tyrannosaurus rex and examined it under a microscope.
Don't tell me they found it.
They found exactly that, a distinct layer of fossilized medullary bone lining the marrow cavity of a T-Rex.
Wow.
This was a monumental discovery for two reasons. First, it proved that non-avian dinosaurs use the exact same complex calcium metabolism mechanisms as modern birds to produce their eggs.
And the second reason?
Second, and practically, it allowed paleontologists, for the first time in history, to definitively identify the sex of a specific dinosaur fossil. Because only females produce medullary bone, that massive T-Rex was unequivocally a pregnant female who died right as she was preparing to lay a clutch of eggs.
That is just brilliant. It's cellular biology confirming paleontology. But once she laid those eggs, what happened? Did dinosaurs just bury them in the sand and abandon them like sea turtles do today? Or did they stick around?
Well, the level of parental care varied wildly across the dinosaur family tree, but many exhibited highly advanced bird-like parenting. The text highlights a legendary discovery made in 1978 by Jack Horner in Montana.
What did he find?
He found a massive communal nesting ground belonging to a large duck-billed dinosaur. He found nests separated by exactly the length of an adult dinosaur, showing they nested in dense colonies like modern seabirds. But crucially, he found the fossilized remains of tiny hatchlings inside the nests, and their teeth were already worn down.
Wait, if the babies are still in the nest, but their teeth are worn down, that means they've been eating tough plant material. But they are too small to leave the nest to get it.
Which means the adults were actively foraging for food, bringing it back, and feeding the nest-bound babies for weeks or months after they hatched. Horner named the dinosaur Maiasaura, which translates to good mother lizard.
Ah, I love that.
Furthermore, we have direct evidence of active brooding sitting on the eggs to keep them warm. In the Gobi Desert, paleontologists found spectacular fossils of an oviraptorid called Sittipati.
I've seen photos of this fossil. It is heartbreakingly beautiful.
It really is. The animal was buried alive by a sudden sandstorm or dune collapse, but it didn't run. It was preserved sitting directly on top of its nest of eggs. Its legs were folded underneath it, and its feathered arms were spread wide in a protective ring over the clutch.
Just like a bird.
It was in a classic, unmistakable birding posture, utilizing the insulative properties of its feathers to physically incubate the eggs. It died protecting its unborn young.
But the text also mentions a counter-strategy called superprecociality. What does that mean?
Right, so while some dinosaurs, like Maiasaura, required extensive parental care, others were born highly independent. In biology, altricial animals are born helpless, like human babies or blind baby robins.
Right.
Precocial animals are born relatively mature and mobile, like a foal walking minutes after birth. The research notes that many dinosaur hatchlings, including those of T-Rex and the small intelligent Troodon, were highly precocial, or even super precocial.
Meaning what exactly?
Their skeletons were heavily ossified at birth, meaning they hatched with strong legs and functional jaws, ready to run and hunt almost immediately without needing their mother's protection.
So a baby T-Rex wasn't waiting in a nest for mom to get back a piece of a triceratops. It was out in the underbrush, hunting large insects or small lizards on its own.
Exactly. And this leads to a fascinating ecological dynamic. Because dinosaurs laid eggs, even the most massive 10-ton adult started its life as a creature no bigger than a house cat. The sheer size difference between a juvenile T-Rex and an adult T-Rex was immense.
Right. Huge difference.
This meant that as a T-Rex grew up, it passed through several entirely different physical phases. A teenage T-Rex was long-legged, slender, and incredibly fast, hunting medium-sized, agile prey. A fully mature adult was heavy, robust, slower, and hunted massive, armored herbivores.
Oh, I see where this is going.
Because they changed so drastically, the juveniles and the adult didn't compete for the same foods. They occupied entirely different ecological niches within the same environment.
That is incredible. The juveniles basically acted as a completely different species of predator until they grew up. All right, we've covered the medullary bone, the brooding, the feathers, the air sacs. The anatomical and behavioral connections to modern birds are completely overwhelming. So let's talk about the exact moment science finally forged the link between dinosaurs and birds, because it happened much earlier than people realize, and it relies on one of the most famous fossils in human history.
It truly is the foundational stone of evolutionary biology. The fossil is Archaeopteryx, and its timing is almost cinematic.
How so?
In 1859, Charles Darwin published his masterwork on the origin of species, which proposed the theory of evolution by natural selection. Darwin predicted that if his theory was correct, the fossil record should contain transitional forms.
Creatures that display a mix of traits from two completely different animal groups.
Right, proving that one evolved from the other. Just 2 years later, in 1861, a limestone quarry worker in Solnhofen, Germany, split open a slab of rock and found exactly what Darwin predicted.
Archaeopteryx, the perfect transitional fossil.
It is the ultimate chimera. Archaeopteryx possessed the jaws full of sharp teeth, the long bony tail, and the three-clawed, grasping hands of a small theropod dinosaur. But preserved flawlessly in the ultra-fine-grained limestone, radiating from its arms and tail, were the unmistakable impressions of advanced asymmetrical flight feathers.
Identical to modern birds.
Identical.
The source material has a detail about Archaeopteryx that I find absolutely hilarious but also incredibly telling. It notes that if those delicate feather impressions had not been preserved in the limestone, we wouldn't have known it was a bird at all.
It's true.
In fact, one specimen of Archaeopteryx that lacked clear feathers was completely misidentified by scientists and sat in a museum drawer labeled as a Compsognathus, which is just a regular, small, meat-eating dinosaur.
It perfectly illustrates the point. The underlying skeletal anatomy of a primitive bird and a small theropod dinosaur are essentially indistinguishable. Beyond the obvious feathers, modern paleontologists have mapped out over 100 highly specific anatomical features that are shared exclusively by theropod dinosaurs and modern birds.
Give me some of the most critical ones.
We can start with the furcula, commonly known as the wishbone. It's a fusion of the two collarbones. For a long time, it was thought to be an exclusively avian structure that acted like a biological spring to aid in power flight.
But it's not.
No. We've now found robust furculae in Allosaurus velociraptor and T-Rex. We also see the semilunic carpal. This is a highly specialized, half-moon-shaped bone in the wrist.
What'd that do?
In a theropod dinosaur like Deinonychus, this wrist bone allowed them to swivel their hands backward in a very specific grasping motion to snatch prey. Through millions of years of evolution, that exact same wrist joint is what allows a modern bird to fold its wings back tightly against its body.
The predatory grasping motion of the dinosaur was exapted to become the wing-folding mechanism of the bird.
Exactly. It's evolutionary recycling. You use the tools you already have to solve a new problem. We even talked about the sleeping postures, right? The small troodontids found in China.
Yes, fossils like Meilong and Sinornithoids.
Right. They were preserved exactly as they died, overcome by volcanic gas or sand while sleeping. They were resting with their legs folded under them, their long tails wrapped around their bodies, and their heads tucked deeply underneath their arms.
Which is the precise posture modern birds use to conserve body heat while they sleep.
It's undeniable. But it brings us to a massive debate regarding feathers. We know the theropods, the meat eaters, had feathers. We've seen them. But did all dinosaurs have feathers? Like, was Triceratops walking around with a coat of fuzz?
That's a great question.
That is one of the most exciting active frontiers in paleontology today. The debate hinges on evolutionary origins. The text explains that we have found simple, hair-like filaments, often called protofeathers, not just in the theropod lineage, but in primitive members of the completely opposite side of the dinosaur family tree.
Oh, really?
Yeah. We mentioned the stiff-tailed bristles on Psittacosaurus, which is an early relative of Triceratops. We found dense coats of filaments on an herbivore called Tian Yulong. Because these feather-like structures appear in two lineages that split apart at the very dawn of the Mesozoic era, many evolutionary biologists argue that feathers, or at least simple beta-keratin filaments, were an ancestral trait belonging to the very first dinosaur.
Meaning the default state of a dinosaur was fuzzy. And some later lineages, like the massive sauropods or the armored ankylosaurs, might have lost their fuzz as they evolved, exactly the same way an elephant or a rhinoceros lost most of its mammalian hair to deal with extreme body heat.
Precisely. The genetic machinery to grow feathers was likely present in all dinosaurs. However, we must be scientifically rigorous and note that there is a dissenting view.
There always is.
It is a very small minority in the paleontological community, but scientists like Alan Feducci have spent decades arguing against the dinosaur-bird connection. They argue that the simple protofeathers found on fossils like Sinosauropteryx are not feathers at all.
What do they think they are?
They believe they are taphonomic artifacts. Specifically, the degraded remains of collagen fibers that existed under the animal skin, which frayed during the rotting process and just happened to look like hair when fossilized.
So they think it's just rotting skin tissue that is being wildly misinterpreted.
Yes. They further argue that advanced flight-feathered animals, like the dromaeosaurs, aren't actually dinosaurs at all, but a separate parallel lineage of flightless birds that evolved convergently.
But most researchers disagree.
Strongly. The vast, overwhelming majority of researchers, geologists, and evolutionary biologists reject this hypothesis. The chemical evidence of beta-keratin in the fossils, the presence of melanosomes, and the sheer volume of overlapping skeletal synapomorphies make the collagen hypothesis mathematically and biologically highly improbable. The consensus remains rock solid. Birds are theropod dinosaurs.
Okay, speaking of the dinosaur family tree, I want to bring up something that has always felt like a massive practical joke played by early paleontologists.
Yeah.
The great taxonomic irony.
Ah, yes. It is one of the classic, bewildering quirks of 19th century scientific classification.
So, when paleontologists first started sorting all these new dinosaur fossils into groups, they noticed a major difference in the shape of their hips. They divided the entire dinosaur family tree into two main branches. You have the Saurischia, which translates to lizard hip dinosaurs like T-Rex and the long-necked Apatosaurus.
Right.
And you have the Ornithischia, which translates to bird-hipped dinosaurs like Triceratops and Stegosaurus.
Correct. The division was based on the orientation of the pubic bone. In the lizard-hip dinosaurs, the pubic bone points downward and forward toward the belly. In the bird-hip dinosaurs, the pubic bone rotated backward, lying parallel to the ischium, pointing toward the tail. This backward-pointing pubis superficially resembles the pelvis of modern birds.
So, logically, to anyone with common sense, you would assume that modern birds evolved from the bird-hipped dinosaurs, right? It's literally in the name.
You would think so.
But no. It's like sorting your digital files into two folders named Vacation and Work. But for some inexplicable reason, you put all the pictures of the beach into the Work folder. Because actual living birds evolved from the lizard-hipped dinosaurs.
It is a wonderful evolutionary irony. Birds are theropods, and theropods are part of the Saurischia, the lizard-hipped branch. The backward-pointing bird-like pelvic structure evolved entirely independently in the actual bird-hipped ornithischians.
That is so confusing.
It's a classic example of convergent evolution, where two unrelated animals evolve a similar anatomical solution, usually to accommodate a larger digestive tract. Meanwhile, the theropods started out with a forward-pointing lizard hip. Over millions of years, as they evolved into birds, their pubic bone slowly rotated backward on its own, achieving a bird-like hip completely independently of the ornithischians.
So the names were just unfortunate timing.
Right. The names, coined in 1887 by Harry Seeley, were purely descriptive of the fossils he was holding at the time, long before the evolutionary lineage of birds was fully mapped out.
So the lizard-hipped dinosaurs slowly evolved into birds. And the bird-hipped dinosaurs, despite having the right name, all went completely extinct. Which brings us, inevitably, to the apocalypse, the single worst day in the history of the planet.
The Cretaceous-Paleogene extinction event, commonly known as the KPG boundary. 66 million years ago, the reign of the non-avian dinosaurs violently ended.
Walk us through the mechanics of doom. Because it wasn't just a rock falling from the sky. It was a cascading failure of the entire Earth system. How does an empire that lasted 160 million years collapse?
The primary kill mechanism is the Chicxulub impact. A bolide, an asteroid, or possibly a comet, estimated to be between 10 and 15 kilometers wide, traveling at roughly 20 kilometers per second, slammed into the shallow ocean of what is now the Yucatan Peninsula in Mexico.
Just unthinkable speed.
The kinetic energy released by this impact is beyond human comprehension. Was equivalent to billions of atomic bombs detonating simultaneously.
The immediate localized effects must have been instantaneous vaporization.
It excavated a crater 150 kilometers wide and 20 kilometers deep in seconds. The impact generated earthquakes that rang the planet like a bell, triggering colossal mega tsunamis hundreds of meters high that scoured the coastlines of the Americas. But the most terrifying immediate effect was the thermal pulse. The impact punched a hole in the atmosphere and ejected trillions of tons of vaporized rock and superheated glass spheres into suborbital space.
And what goes up must come down.
Exactly. When that ejecta rained back down through the atmosphere across the entire globe, the friction caused them to act like trillions of microscopic shooting stars. This superheated the upper atmosphere to oven-like temperatures for several hours.
Oh my God.
The thermal radiation baked the surface of the Earth, igniting global firestorms that burned massive swaths of the terrestrial forest to ash. Any unsheltered animal on land that could not burrow deep underground or dive underwater was killed in the first 24 hours.
It's horrific. But the asteroid couldn't burn every single inch of the planet. The real killer wasn't the heat. The real killer was the cold and the dark that followed.
Yes. The thermal pulse was followed immediately by an impact winter. The rock the asteroid hit in Mexico was rich in gypsum, which vaporized and injected massive quantities of sulfate aerosols directly into the stratosphere. Combine that with the soot from the global wildfires, and you have an impenetrable veil covering the planet, reflecting sunlight back into space. The Earth plunged into a deep freeze.
And when you block the sun, you stop the biological engine of the planet.
You shut down photosynthesis. With no sunlight, the phytoplankton in the oceans die, and the broad-leafed plants and forests on land collapse. When the primary producers disappear, the food web completely unravels from the bottom up.
So the herbivores go first.
Right. The massive herbivorous dinosaurs, the multi-ton triceratops, the ankylosaurs, the remaining sauropods run out of food and starve to death. And once the massive herbivores starve, the giant apex predators, like Tyrannosaurus rex, have no prey. The terrestrial ecosystem simply couldn't support large-bodied animals anymore.
But the research points to a second factor. The asteroid wasn't acting alone. The Earth was already tearing itself apart.
Yes. The Earth was experiencing a period of extreme geological stress. On the exact opposite side of the planet from the impact, in what is now India, massive flood basalts known as the Deccan Traps were erupting.
Right, volcanoes.
But these weren't explosive cone volcanoes like Mount St. Helens. These were massive fissures in the Earth's crust, spewing unimaginably huge lakes of lava over tens of thousands of years.
And volcanoes don't just release lava, they alter the chemistry of the sky.
The Deccan traps pumped colossal amounts of carbon dioxide and sulfur dioxide into the atmosphere. This was driving extreme, chaotic global climate fluctuations, periods of intense greenhouse warming, followed by rapid cooling, along with severe ocean acidification and acid rain. The ecosystems were already deeply stressed.
But wait, the source material mentions a terrifying connection between the two. If the asteroid hit in Mexico and the volcanoes were erupting in India, how are they related? Did a rock hitting the ground make a volcano erupt thousands of miles away?
It comes down to planetary seismology. The Deccan traps had already begun erupting before the asteroid hit, but recent mathematical modeling suggests a concept called antipodal focusing. When the Chicxulub asteroid impacted Mexico, the seismic shock waves traveled through the Earth's crust and mantle. Because the Earth is a sphere, those seismic waves converged and focused their energy on the exact opposite side of the planet, the antipode, which happened to be India.
So it was like hitting a cracked windshield with a hammer.
Exactly.
Ah.
The massive seismic jolt from the asteroid converging on the Deccan Trap's magma chambers acted as a massive decompression event. It squeezed the sponge. Geologists have found that the most voluminous, catastrophic pulses of lava from the Deccan Traps occurred almost immediately after the Chicxulub impact.
Wow.
The asteroid essentially turbocharged the volcanic apocalypse. It was a synchronized 1-2 punch that completely broke the biosphere.
Okay, so the sky is dark, the plants are dead, the food web has collapsed, acid is raining from the sky, and lava is flooding a continent. Here is the ultimate question. If the planet was a hellscape, why did any birds survive? If birds are dinosaurs, why didn't the ancestors of pigeons and hawks die alongside the T-Rex?
The answer lies in highly specific ecological niches and dietary adaptations. The non-avian dinosaurs were completely dependent on the leaf-based food web. Furthermore, there were archaic groups of birds living at the time, like the Enantiornithines, which were highly successful, toothed birds that lived in the trees.
Okay.
When the global firestorms burned the forests and the impact winter killed the leaves, the habitat and food source for the non-avian dinosaurs and the tree-dwelling archaic birds vanished. They went extinct. But the ancestors of modern birds, the Neornithes, had a crucial survival mechanism.
They weren't eating leaves or relying on trees.
Precisely. Many of the early modern bird lineages were small, ground-dwelling, and crucially, they had evolved toothless beaks specifically adapted for eating seeds. Yes, a seed is essentially a tiny, highly nutritious, durable survival capsule designed to weather harsh conditions. Even if the adult forest dies, billions of seeds remain viable in the soil for years.
Oh, that's brilliant.
When the impact winter hit and the leaves died, the small, grain-eating, ground-dwelling birds could sift through the ash and dirt, finding enough high-energy seeds to survive the years of darkness. Their small body size meant they didn't need many calories, their feathers kept them warm in the freezing impact winter, and their diet of seeds bypassed the collapsed leaf-based food web.
And then the sun came back.
Once the dust finally settled and the sun returned, those few surviving seed-eating lineages radiated rapidly to fill all the empty ecological niches left behind by their extinct cousins.
That is profound. A 10-ton triceratops starves to death, but a little ground-dwelling bird pecking at seeds in the ash makes it through the apocalypse. Now, before we close out, there is a lingering debate in paleontology mentioned in the text. Did any non-avian dinosaurs make it past the asteroid? Is there proof of Paleocene survivors?
It is a highly contentious area of geology. The text details the discovery of a single hadrosaur femur, a duck-billed dinosaur thigh bone, found in the San Juan Basin in New Mexico. The rock strata it was found in dates to the Paleocene epoch, about 64.8 million years ago. That is over 1 million years after the asteroid hit.
Does that mean a localized population of non-avian dinosaurs somehow survived the fallout and limped along for another 1 million years?
Well, a few researchers initially argued exactly that. However, the vast majority of geologists and taphonomists look at the condition of that bone and argue that it is reworked.
What does reworked mean?
It means the dinosaur died in the late Cretaceous before the asteroid hit and was buried in sediment. Millions of years later, a river cut through that landscape, eroding the original Cretaceous rock, washing the fossilized bone out, and tumbling it downstream until it was reburied in much younger Paleocene-era sediments.
So it's a geological illusion.
Yes, the bone is old, but the grade is new. As of today, despite decades of searching, there is no universally accepted, definitive proof that any non-avian dinosaur survived past the KPG boundary.
The empire fell. The non-avian dinosaurs died out, but their legacy completely saturated human culture the very moment we started pulling them out of the ground. Okay, we have covered a staggering amount of time in biology today. Let's summarize the journey we just took. We started by stripping away the word dinosaur from the swimming plesiosaurs and flying pterosaurs, locking down that specific, highly efficient, erect-stanced archosaur hip. We watched human understanding evolve from ancient Chinese apothecaries grinding up dragon bones to the medieval Europeans imagining biblical giants. We waded through the explosive dynamite-fueled hostility of the Bone Wars and pushed into the dinosaur renaissance, where John Ostrom looked at the stiff tail and sickle claw of Deinonychus and finally forced the dinosaurs to stand up, shake off the swamp mud, and start running with hot blood.
It's an incredible history.
And we looked at the sheer impossibility of the soft tissue revolution using scanning electron microscopes to see the rusty red countershading of a Sinosauropteryx, mapping the internal organs of Scipionix, and dissolving ancient bone to find the actual microscopic elastic blood vessels preserved inside the thigh of a Tyrannosaurus rex.
This amazing discoveries.
We scaled their avian biology up to the mind-boggling 170-ton Boeing 747-sized dimensions of Bruchithiasaurus, relying on hollow bones and unidirectional air sacs to keep from overheating, and we shrank them down to the 1.8-gram bee hummingbird. We heard them booming low-frequency infrasound through closed mouths, we watched them brood over their nests using medullary bone to fuel their eggs, and finally we watched the sky catch fire and the world freeze, leaving only the resilient, seed-eating, feathered survivors to inherit the ashes. The pigeons, the crows, the hawks outside your window. They are the dinosaurs.
His remarkable narrative of evolutionary resilience and adaptability. And reviewing all this material leaves us with a profound realization about the nature of the fossil record itself.
What is the ultimate takeaway here?
Well, we spent a lot of time discussing the Johol biota and those incredible conservation Lagerstätten. We rely entirely on those highly specific, incredibly rare anoxic lake beds to preserve the fragile feathers, the vibrant melanosomes, and the soft tissues of Mesozoic dinosaurs. Without those few mathematically improbable deposits, we would still think they were just scaly, gray, sluggish lizards.
We would have never known the truth.
Exactly. So project this reality forward. Imagine a future intelligent species millions of years from now, long after humans in our cities are gone. If their paleontologists dig up the fossilized remains of today's avian dinosaurs, our modern birds, what will they find?
Just the bones.
Right. The fossil record is notoriously cruel to soft tissue. Feathers rot, pigments dissolve, keratin beaks detach and disintegrate. If those future scientists only find the bare mineralized bones of a peacock, a flamingo, or a parrot, what completely brilliant, colorful, and complex parts of their biology will be lost to the stone?
Wow.
Without their own lucky Lagerstätten deposits, will they look at the skeleton of a macaw and assume it was just a drab, gray, scaly reptile?
That is a haunting and beautiful thought. It makes you realize how much majesty and vibrant life we are still missing from the Mesozoic, locked away where the stone couldn't preserve it. Next time you're outside, look up into the trees, look at the starlings, the eagles, the sparrows, watch the dinosaurs fly. You are not looking at a standard definition broadcast anymore. You are looking at the intricate, complex 4K reality of a dynasty that never really ended. Thanks for taking the plunge with us today.